so my thinking on these before we get started. AP Central has taken away waves, and they've just allowed this bare sliver of oscillations on the test. Now, you would think it odd that I would start with, we're getting ready for the AP test with an oscillation problem, but A, we're still covering oscillations, and B, and this is kind of important, there has never been a test where they did not feature waves and oscillation. It is very odd they saved this chapter. So it feels like this chapter is likely going to be the chapter, if that makes sense. So there's a chance that the test will be on something like this, and they'll justify themselves by saying there'll be a force problem, an energy problem, and a blah, blah, blah problem, and an oscillation problem. They'll get them all in with a simple spring mass system. Okay, so first of all, let's talk about this particular problem. Hopefully you have it. I have a 5 kilogram mass that I've stapled to a spring. I put a 3 kilogram mass on top of it, and the first thing we're going to do is let go of it. And what would happen? Well, the spring can't hold it up unless it's compressed, right? It doesn't provide any force at all until it is squished. So step one, what's going to happen is this thing is going to, whoops, I need a pen. That would be great. Step one is it's going to shrink down. It's going to get skished until the force of weight is equal to the force of the spring. Now it's going to go past that point. It's going to go squish down even more. Then it's going to go up and down, up and down, up and down, up. And in the real world, eventually it'll reach the point at which the amount it's squished is equal to the amount it's pushing up. Okay? And we call that point equilibrium. And we're going to have to calculate that. I'm just going over the problem right now. Now, this would be down a distance, right? Because the spring needs some oomph to hold it in place. Second thing they're going to ask you to do, they're going to say, okay, I'm going to pull it down some more and let it oscillate. You know how to calculate that. When it oscillates, it's going to go up and down. It's going to go past this equilibrium point, the height it originally started at, right? So, sorry. Oh, I just said that completely wrong. So take that, remove that from your brain. This is the equilibrium point now. So when I push it down, it's going to go up and down an equal amount above and below this equilibrium point, the place where it was equal forced, right? Because at that point, it's not being forced up or down, so that it could sit at rest there. If you push it down, it's got to get pushed back up. The spring's going to push it back up. If it goes past that point, the gravity and the spring will pull it back down. Okay? Now, the next question they ask is kind of interesting. They say, well, when the spring, how far can you push it down? So actually, the first question is, what's the acceleration? The maximum acceleration, these two blocks would stay together. Well, the interesting part about that is really simple. It is that the blocks, this block here, can't get pulled down more than 9.8 meters per second squared. Or the little block can't keep up with it. Why? Because it's not tied on. So when this thing gets pulled down more than 9.8, remember this block is falling. If it's not falling fast enough, if it's got like 7 meters per second squared of acceleration in the bottom block, then this thing is pushing it down. But if this thing gets pulled down at 9.8, this thing's going to pop up, right? Because it can only fall so fast, and that's 9.8, so it's not attached. Okay? So we're going to stipulate that 9.8 meters per second squared is the maximum acceleration you can have before it pops off. Then it's going to ask where. Now I'm going to solve it the oscillation spring way. Before I do that, though, you could reason this out. What do you mean? Well, here's what happens. If the spring gets back to this position here, right, gets back up to that position there, the pre-squished position. If it gets past that point there, then what happens is the spring starts pulling down, right? Because right here, the spring not pulling up or down. Weight's pushing it down. Weight's what makes it go down to this position here, right? But if, big if the spring goes past that point on its way back up, then what's going to happen is the spring will pull it down. So the weight will pull it down and the spring will pull it down. That means it's going to be greater than 9.8, which means this thing is going to not fall at the same rate, and this thing's going to get pulled down faster than this, so they're going to separate. And so the answer is going to be the original position before anything got squished. Okay, that's what the answer is going to be. All right, all that said, let's do it for realsies now. All right, so the punchline is we're going to go ahead and do the problem now. So step A. Step A asks, when the blocks are at rest, how much is the spring compressed from the original height? Okay, so we look at the problem, and the reasoning is the only way it can be at rest is if there's no acceleration. If there's no acceleration, means the net force is equal to 0. So net force equals sum of all forces. MA is therefore equal to, I have force of spring pushing up and force of weight pulling down. Acceleration 0, so that side goes to 0. Force of the spring is Kx minus force of weight, which is going to be 8 times 9.8. K is 1,000. So I'm going to do some fancy math here. 8 times 9.8. Hopefully I'm not using a calculator for that, but I am, so I'm embarrassed for everybody again. Sorry about that. Minus 78.4, so I divide that by 1,000, and I get 0.0784 meters. And that's the correct answer for that question there. Okay, so in other words, the forces are equal because if the thing's not moving, it has to have no acceleration, right? So it's sitting there. If it's sitting at rest, that's what it's doing. Okay, determine the frequency of oscillation. This should be child's play for you childrens. There is one formula for periods of oscillation, and it's period equals 2 pi. This is a mass spring. Yes, find the mass spring version of it. It is m over k. This becomes 2 pi. M is 8. K is 1,000. Slap this in my calculator, and I'm going to get 2 times pi times parentheses 8 divided by 1,000 square root. Boom, baby. I got point. Oh, where's my pen? My pen. I lost my pen. Come on, there it is, right there. Okay, so no, it glows for you guys. You're probably like, what is he talking about? The pen's right there. It's really obvious. It's not obvious to me. So that's seconds. But that's not the question to ask. The question to ask, what's the frequency? And frequency, one thing we know of frequency is 1 over the period. So therefore, 1 divided by shift answer gives me a whopping 1.78 hertz or per second. HZ, that I'm HT, I have no idea what. Okay, try it. All right, determine the magnitude of the maximum acceleration that the blocks can attain and still remain in contact at all times. Well, I made the argument before. If the top block has to fall faster than 9.8, it's got nothing else pushing on it, so it's done. The only thing it can have is weight. Weight's pushing it, making it accelerate 9.8. The bottom one gets pulled out from under it faster than 9.8, then it's not going to make it. 9.8 meters per second squared, I would say acceleration should be greater than or equal to that. And I'd throw the word down on here because it makes me really nervous to say greater than negative 9.8 because that implies positive numbers work. And positive numbers wouldn't work. Shoving it up, the thing is going to stay on there for certain, right? Okay, how far does spring be compressed beyond the part of the... Now the answer is going to be 0.074 beyond the equilibrium point, right? It's going to be that, right? Because we know that's the point at which the spring gets back up to full length and it's got to start pulling the block down. That said, we can solve for that, can't we? How do we solve for that? We're going to say, hey, when is acceleration? F net equals the sum of all forces. MA is equal to, what forces are pushing on it? We have simply Kx. Now, you think, but Mr. Rossi, there's weight on it, there's other things like, yes, but we've already, when we say the equilibrium point, we can now treat the spring as already adjusted for weight, okay? And so as such, we don't have to worry about that at all. We're just going to slap in an 8 over there, 8 times 9.8. Over here, we're going to 1,000 times x, so x equals 0.0784 meters. And again, once you have a mass spring system, the middle point is the place at which, the place where the equilibrium point has been squished that much. There's no net force there. So the spring, you can treat it as a spring going up and a spring going down because weight's already been canceled out. As long as a block doesn't fall off or something crazy like that happens. Okay, if you really, really don't like it, just remember once it gets up to the maximum length, the spring's going to start pulling down. Let's get back to its normal length, right? The spring's going to start pulling down and the top block's going to pop off because the bottom part's going to be pulled down when the top block is. Okay, determine the maximum speed of the blocks as a compressed distance found in part D. So let's say we push it down that far. So we're going to push it down from its equilibrium position. We're going to push it down from there. So 0.784, we're going to push it down another 0.784 and let go of it. Okay, so we're just going to end up going, all right, so we want to know what's its energy? Well, its energy at the bottom, so energy before equals energy after. Energy before is equal to a compressed spring. Energy after is going to be equal to kinetic energy. Okay, how far did we compress the spring past the equilibrium place? Remember the first part we got for free. It's going to be 1,000 times we push it down another 0.784. This distance here, how far we pushed it down. That's the max, so it's compressed. After that, it's going to go back up and decompress, right? 1/2, what's my mass? My mass is 8, so I know what my speed is. So I solve for V, and that would be in the middle spot when it goes back through the equilibrium place. Okay? I'm doing the best I can. I hope you're with me. All right. If not, ask for another video. I think I've made this video like 4 times now. Getting good at it. Probably getting too good at it. That's probably going faster than I should. Divided by 4 to the 0.5. I feel like this answer is much larger than I got before. That's disturbing. Oh, yeah, nope. That looks good. Divided by 4. Yeah, that. Oh, no, not divided by 4. It's divided by 8. Darn it. Okay, so let's try this again. I can do this. 1,000 times 0.784 squared divided by 8, because I canceled out the half earlier, 0.5, and I get 8.77. 8.77 meters per second. Hopefully that's the same answer as I got before. So anyway, that is the truth, okay? All right, so that's how to do this problem. It is nasty. Try the next problem. And again, if you need help with it, let me know. I'll be happy to do more videos.